Good morning, good afternoon. I am delighted to welcome you to today's webinar, which is part of the Knowledge Across Borders series with our friends at the Chinese Academy of Sciences. My name is Professor Anthony Long, and I'm the Acting Vice-Chancellor of Durham University. I will shortly introduce our distinguished experts, Professor Tianjin Zhou from the Institute of Atmospheric Physics at the Chinese Academy of Sciences, and Professor Glenn McGregor from the Department of Geography here at Durham University. Today's webinar is already the fourth in our successful series, with previous talks covering areas such as paleontology, cosmology, and interdisciplinary research. Previous events have been enjoyed by people from over 40 countries, and it's fantastic to see today that we again have people joining us from all over the world. This series has come about as a result of our long-standing research partnership with colleagues and friends at the Chinese Academy of Sciences, or CAS for short, which goes back more than 35 years. Researchers at Durham and CAS have been working together on a wide range of research areas, including climate change, astronomy, resilience to natural disasters, and so on. Both of our organizations are committed to pushing scientific boundaries in order to find solutions that can benefit society. And of course, it's very apt that the topic of today's webinar is climate change and health, with only a few weeks to go before the start of COP26, with countries updating their plans for reducing emissions. There is growing evidence that many of us are aware of the effects of climate change in the form of increases in wildfires, in flooding, and heat waves. And these extreme events are causing catastrophic harm to society and people's livelihoods, their health, and their well-being. Unless action is taken, the impacts of climate change will continue to be substantial. Today's speakers are at the forefront of climate change research. Both are lead authors for the Intergovernmental Panel on Climate Change, or IPCC's sixth assessment report. They will present the scientific evidence for humans' influence on climate and describe possible climate futures under global warming. They will also outline some of the projected impacts of climate change on health, with an emphasis on heat-related effects, and present some possible solutions for living in a world that is likely to experience more temperature extremes. I hope very much that the presentations will stimulate new ideas and will open up new ways of thinking. So thank you again for joining us, and it's my pleasure to now hand over to Professor Yaping Yang, Vice President of the Chinese Academy of Sciences. Thank you.
Respected Acting Vice Chancellor Anthony Long, Pro Vice Chancellor Claire O'Malley, Professor Glenn McGregor, Tianjin Zhou, and Junjie Wu, dear colleague and friend. I'm Yaping Zhang, Vice President of Chinese Academy of Sciences. I'm sending my best regard from Kunming, China, where UN Biodiversity Conference, CBD COP15, is currently in session. As we all know, besides COP15, an equally important event, COP26, will soon be held in Glasgow this November. Nowadays, every region on our Earth has been affected by climate change in multiple ways. There is an urgent need for international commitment and global action to address this challenge. The forthcoming COP26 session will be a critical milestone. CAS and Durham bear the same responsibility for helping to solve the global issues through scientific research, and we have a long history of deep cooperation across a wide range of fields, including climate science. With shared idea and joint efforts, CAS and Durham have co-organized today a knowledge cross-board webinar titled Climate Change, Extreme Event and Health Risks. I hope the webinar will share our knowledge on climate change and health, climate adaptation, and mitigation. I also hope it will provide more opportunity for future cooperation in climate science. Last but not least, I would like to extend my gratitude to Professor Nang and Professor O'Malley, to our two speakers, and QA chair, Professor McGregor, Zhou and Wu, and to the organizers of this webinar. I would like to thank all the participants attending today. I hope you will enjoy the event. Thank you.
Thank you very much, Professor Yaping Yang, for those kind remarks. We are delighted to be working with you and your colleagues at CAS on both fundamental and world-changing research. Now, we'll shortly hear from our experts, but before we do, we'll play a short video we've prepared to celebrate our partnership with the Chinese Academy of Sciences.
As dedicated pioneers of groundbreaking research, Durham University and the Chinese Academy of Sciences are working together to push the limits of scientific exploration. We are committed to international collaboration, creating scientific solutions to understand our world and beyond. The Chinese Academy of Sciences, China's driving force in exploring natural sciences and harnessing technology. Durham University, a globally outstanding centre of teaching and research, inspiring our people to make a world-changing difference. We share common ground. Both centres of world-changing research and innovative teaching, both with a commitment to interdisciplinary research, producing practical solutions to real-world problems. Energy to astronomy. Surface science to climate change. Together, we are stronger and will achieve so much more. We will stimulate fresh ideas, open up new perspectives across intellectual and geographical boundaries, and create a better understanding of the big scientific questions. We will inspire you to explore how science can improve the world and change our lives. We invite you to join us.
Terrific. It's now my great pleasure to briefly introduce our two speakers to you. First, we will hear from Professor Qianqing Zhao, who is a senior research scientist in the Institute of Atmospheric Physics at the Chinese Academy of Sciences and professor at the University of Chinese Academy of Sciences. He works on climate modeling and climate dynamics and how the climate system responds to anthropogenic and natural forcing agents. Qianqing served as lead author on the 5th and 6th assessment reports by the Working Group 1 of the Intergovernmental Panel on Climate Change. He's also a member of the Climate and Ocean Variability, Predictability and Change Working Group on Coupled Modelling, as well as a member of other leading working groups within the field. After that, we'll hear from Professor Glenn McGregor, who is a professor of climatology in the Department of Geography here at Durham University. Glenn is also the principal of Ustanov College, which is our sole postgraduate-only college here in Durham. His research focuses on synoptic climatology, biometeorology, hydroclimatology, and climate and society. Glenn is Working Group 2 lead author on the 6th assessment report on climate change for the IPCC, a member of Public Health England's Health Protection Unit's Research Advisory Board, and steering committee member for the Global Heat Health Information Network. Glenn was also a lead author for the IPCC special report on extreme events and a contributing author on the IPCC's 4th assessment report. Previously, Glenn has served as a chief editor of the prestigious International Journal of Climatology and was the World Meteorological Organization's lead expert for climate and health. I hope that these short introductions give you a glimpse of the tremendous expertise our speakers have in their fields. After their presentations, a Q&A session will be chaired by Professor Junji Wu, who is our Deputy Executive Dean in the Faculty of Science at Durham University. I hope very much that you enjoy this webinar, and I'll now hand over to Professor Qianqing Zhao. Thank you.
Thank you. Good morning or good afternoon, dear friends. Today, we will talk about climate change, extreme events, and health risk. At the beginning of this talk, first, I will answer one question you might ask. What is climate extreme? And here is the definition from the glossary of IPCC AR6. It's defined as the occurrence of a value of weather or climate variable above or below a threshold value near the upper or lower ends of the range of observed values of climate variable. Please note both extreme weather events and extreme climate events are referred to as climate extremes. And here is the probability density function of daily temperature. You can find extremes are always located in the tails of this kind of curve. And here is the case for precipitation. Can we observe climate extremes in the real world? Here, I show some examples. The first is the observed extreme rainfall and flooding occurred this year in Germany. Here are some pictures from the media. It's for July 19th of this year. You can find the terrifying flooding in the western part of Europe had led to a mortality of nearly 200. This year, we also observed similar extreme events in China. And here is the example of the so-called catastrophic flooding in Henan of China on July 20th. And here is the picture for the railway station in Zhengzhou, the province, the capital of the Henan province. And here is the downtown of Zhengzhou. In observation, the hourly rainfall here is larger than 200 millimeters. The 3 days total rainfall is above 600 millimeters. Please note for mean state here, the climatological annual mean rainfall is only about 600 millimeters. Based on the statistic, the official deaths of from the floods has reached nearly more than 300. This is the case occurred in China. Only last week, south to Beijing in Shanxi province, there was another extreme event. It occurred on October 2 to 6. And here is the picture from the media. On October 9th, the Fenghe River in Shanxi province burst its bank. And you can also find the railway bridge is damaged by the flood on October 7th. Based on the news from the China Daily, more than 1 million people are affected by this flooding, and more than 20,000 residents in this area have been relocated after the heavy rainfall. In addition to the extreme precipitation, we also observe heat waves in our life. Here is one example for the so-called historical heat wave in North America occurred on June 30th this year. You can find the surface temperature is about 40 degrees. So after you see all these observed pictures, one question you might ask is, why did these events happen? The answer is given by the IPCC AR6. Recent changes in the climate are widespread, rapid, and intensifying, and also unprecedented in thousands of years. Behind this assessment, we have many evidence. What I show here is the global warming over the instrumental period. You can find starting from the end of the last century to the recent decades, the global warming is happening. Based on the statistic, global surface temperature was more than 1 degree in the recent decades than the pre-industry era. If we extend the record to the past 2,000 years, you can find the human influence has warmed the climate at a rate that is unprecedented in at least the past 2,000 years. This is the case for the long-term change of temperature. If we examine the surface pattern of the warming trend, and here we show the trend in the early decades and in the recent decades. You can find first, the warming has accelerated after the 1970s. Second, the land is warming faster than the ocean. And third, if we focus on the Arctic, you can find it has warmed at more than twice the global average of the past about 50 years. How about the case of China? What I show here is the enemy surface temperature average over China, and we also compare it with the global average. You can find the average warming over continental China is larger than the global mean condition. If we focus on the regional features, you can find the warming over the Tibetan Plateau and North China are far stronger than other parts. The plateau is warming at a rate about twice as fast as the global average. Actually, we even have more evidence. The changes are occurring throughout the climate system. The evidence are given here. First, in the atmosphere, you can see the concentration of carbon dioxide is increasing. The precipitation has changed over many parts of the world. If we extend our eyesight to the cryosphere, you can find a reduction of the glacial mass loss. If we focus on the biosphere, we can find similar changes. And also, we focus on the ocean. We found the increased global surface temperature, the increase in global sea level, and also the ocean heat content. So based on all this evidence, you see changes are occurring throughout the whole so-called climate system. So after seeing all these observed changes, another question you might ask is, are the observed changes natural or anthropogenic? The answer I give here is also from ITCCAR 6. It's indisputable that human activities are causing climate change, making extreme climate events, including heat waves, heavy rainfall, and droughts more frequent and severe. To support this conclusion, we need climate modeling and detection and attribution studies. What are climate models? Climate model actually is a digital twin of the Earth. It can help us to understand the past change and also project the future changes. And here is a photo from Professor Suki Manabe. He is regarded as the father of the first general circulation climate model in the world. We know he was awarded the Nobel Prize in Physics this year. Based on the models, we can do experiments in supercomputers. And here is the result of global mean surface temperature in observation and also in the simulations. We have done 2 sets of simulations. The result for the human-induced and also natural forced components here are shown in brown. And also, if we only specify natural drivers, what I mean is solar and volcanic activities, we can get the result of the time series in green. You can find the observed warming trend can only be seen in the brown colors. That means only when we specify the human influence can we reproduce the observed warming? This strongly suggests the warming in the past more than 100 years was caused by anthropogenic forcing agents. However, this kind of visual inspection is not enough. We need quantitative estimate. For this purpose, we need to detect the human activity. In other words, we need to try to find the fingerprint of the human influence. Because the observed changes are caused by both natural and anthropogenic factors, as shown here. So, determining the cause of the detected warming trend needs method of attribution. I hope to highlight here that in this regard, we have used the so-called optimal fingerprint technique method. And the pioneer of this kind of approach is from Professor Klaus Hasselmann. He was awarded Nobel Prize in Physics also in this year. By using the so-called detection and attribution method, we can make a quantitative comparison estimation of the forcing agents. What I shown here, and this is the observed warming during this period relative to the pre-industry area. You can find the warming is more than 1 degree. And here is the attributed warming. You can find the attributed warming is nearly exactly the same as the observation. And here is the contribution from well-mixed greenhouse gases. You can find the warming is stronger than the observation. However, for the contribution of aerosols, you can find a cooling trend. So it partly offsets the greenhouse gases induced warming. And finally, we get an attributed warming nearly exactly the same as the observation. So based on this kind of observation, detection, and attribution studies, in AR6, it's summarized that observed warming is driven by emissions from human activities, with greenhouse gas warming partly masked by aerosol forcing. We can also make quantitative estimation for different contributors. And here is the result summarized in the SPM or IPCC AR6. For the global surface temperature increase from the pre-industry area to the recent decades, you can find the likely range of total human caused part is about 0.8 to 1.6 degree, with a best estimate of about 1 degree. For the contribution of well-mixed greenhouse gases, the range is from 1 to 2 degree. For the contribution of other human drivers, especially aerosols, the contribution of the cooling from 0 to 0.8 degree. For the contributions of natural drivers and the net internal variability, you can see they are small. In addition to the mean state changes of precipitation, we also observe the changes in the extremes. And here is the result of the observed linear trend of heat extremes. You can find in the annual hottest temperature, annual coldest temperature, and also the number of days exceeding 90th percentile. All we can observe an enhanced trend. These are the results for the observed heat extremes. We can even do event attribution. Here, I would like to show a case study for the record-breaking monthly scale nighttime heat wave occurred in Northeast China in the summer of 2018. You can find the extreme temperature index here is nearly 4 degrees. This cartoon is from the local media in the city of Dalian. We can do event attributions. And the red curve here are the PDF distribution of the experiments with anthropogenic influence, while this curve is the result for without anthropogenic influence. You can find the increased probability of such kind of extremes. We can also estimate the return period of such kind of event in the world with or without human activity. So based on this kind of event attribution, we conclude the persistent nighttime heat waves like the event of summer 2018 in Northeast China are extremely rare in the natural world, but now have become about a once in 60-year event with anthropogenic warming. This is the case for event attribution. We have more evidence. This figure is from IPCC AR6. Climate change is already affecting every inhabited region across the whole globe, with the human influence contributing to many observed changes in weather and climate extremes. What I show here is for the hot extremes. Please note this color indicates an increase of the observed hot extremes. More dots means more confidence. And here is the case for European countries, and here are the results for Asian countries. You can find over most part of the world, the extreme hot events are increasing, and this kind of increasing is due to human activity. How about the case of heavy precipitation? Again, here I show similar figures. Please note this color indicates an increase of extreme precipitation. You can find although the confidence is not so high as temperature, still in many parts of the world, we can find increase of the extreme precipitation. So based on this evidence for the past observed changes, next question I guess you will ask is, what will our climate look like in the future? How about the future climate change? Climate change is already affecting every region on Earth in multiple ways. The changes we are experiencing now will increase with further warming. However, we have a choice actually. We can either live in a world with global warming at 1.5 degrees, or we can live in a world at about 4 degrees global warming. Climate scientists can help us to project future change. Here, I show the result of so-called scenario-based climate projections. The so-called SSPs are used at IPCC AR6. We have different scenarios from very high to middle to low and very low scenarios. You can find for the emission of CO2, very high emissions, of course, is very high. For this scenario, the peaking of the emission will be around 2018. In the very low emission scenario, however, the net zero emission will be around 2016. Please note, future emission cause future additional warming, but the total warming is dominated by the past and the future emissions of greenhouse gases. How about the projected changes? And here is the global surface temperature relative to the pre-industrial area projected by different scenarios. It's not surprised to see, following the high emission scenarios, we will have a far warmer world. You can find the global surface temperature will continue to increase until at least the end of the middle century, and all emission scenarios we considered. And here is the line of global warming at 1 1 degree and 2 degree. And you can find global warming of 1.5 and 2 degree will be exceeded during the 21st century unless deep reductions in greenhouse gases and other CO2 and also other greenhouse gas emissions occur in the coming decades. So the result are scenario dependent. And here is the result for global average. You can find we can either live in a world below 2 degree, below 3 degree, or even below 5 degree. And here is the observed changes up to the recent decades. You can find we are not far away from 1.5 degree warming and also not far away from 2 degree warming. Another point for the projection I hope to highlight is with every increment of global warming, the changes will get larger in regional mean temperature. And here is a special patterns of surface temperature under 1.5, 2, and 4 degree global warming. You can find across 3 warming levels, the land areas warm more than the oceans, and the Arctic and the Antarctic warm even more faster than the tropics. How about the case of regional precipitation? Again, this is a similar picture except for the precipitation. You can find precipitation is projected to increase over high latitudes and also the equatorial Pacific and part of the monsoon area in Africa, Asia, and also part of East Asia. But the precipitation will decrease over part of the subtropics and also in limited areas of the tropics. How about the extremes? Here, I show the result of hot temperature extremes for 1 in 10-year event. This is the change of frequency, and this is the change of intensity. First, please focus on the world under 1.5 degree warming. You can find the 1 in 10-year event of hot extreme in the pre-industry area will likely occur more than 4 times under 1.5 degree warming. And also the intensity will be about 1.9 degree hotter. Under 4 degrees of global warming, such kind of event will likely occur 9.4 times. And also the intensity will be about 5 degrees hotter. And here is the result for 1 in 10-year heavy precipitations. You can find for the 1 in 10-year event occurred in the pre-industry area, under 1.5 degree, it will likely occur 1.5 times. And also the intensity will be 10% wetter. And the global warming at 4 degree, it will likely occur 2.7 times. And also the intensity will be 30% wetter. How about the monsoon precipitation changes? Here we show the result of global monsoons. Please note the global monsoons includes the Asia, South Asia, East Asia, part of Australia, Africa, and a part of the North America and the South America area. Here we show the 1 in 20-year event of extreme rainfall in the recent years. You can find following global warming from 1.5 degree to 2 degree, 3 degree, and 4 degree, we get cooling colors. That means we will have shorter reaching period. We also can estimate the likelihood of heat extremes. In the year of 2015, we have record-breaking extremes in Africa. You can find the surface temperature is pretty high, it's record-breaking. And here is the probability of such kind of event under global warming at 1.5 degree and 2 degree. You can find also the difference between 1.5 and 2 degrees is only half a degree. However, the half degree less warming will reduce the probability of such kind of event by about 10%. So, after showing all this information, the last question you might ask is, what's the implication of all this information? I hope to highlight we need to limit global warming. For this purpose, a large-scale reduction in greenhouse gases emission are needed. So up to now, I have shown evidence mainly from the physical science perspective. Next question you might ask is, how about climate change and human health? This question will be answered by Glenn. Glenn, please welcome.
Thank you, Tianjin, for that excellent overview of the science of climate change. From what Tianjin has described to us, it's very clear that something is happening to our climate, and under the human influence of climate change, something will definitely happen to the climate. And this is just a reminder of some of the projections shown by Tianjin in his presentation regarding the likely changes in temperature, regional temperature change under different warming scenarios for temperature, and again for precipitation. Now, of course, these projected impacts have made us worry about the possible impacts of human-influenced climate change on health. Now, worrying about the relationship between climate and health is not a new thing. If we go back to 400 BCE, Hippocrates was writing upon the influence of air, water, and situational place, the location where we live, and the importance of these things for our health. He wrote about the health implications of the seasons of the year, the impacts of hot and cold winds on health, the qualities of the waters, and the unique setting of in the landscape of a city. Now, this recognition of the nexus of air, water, and situational place 2,400 years ago, in many ways laid the foundations for the contemporary disciplines of biometeorology and environmental health. And of course, the study of the relationship between climate and health. And of course, an important context for worrying about the relationship between climate and health is the likelihood that the globe will warm by 1.5 degrees, if not 2 degrees, if we do not take action to reduce the likelihood of warming. And this is encapsulated in the so-called Paris Climate Agreement, the central aim being to strengthen the global response to the threat of climate change by keeping global temperature rise this century well below 2 degrees Celsius above pre-industrial levels, and to pursue efforts to limit temperature increase even further by 1.5 degrees. Now, the implications of not meeting these targets have been made very clear in the IPCC's special report on global warming and the impacts from an increase in temperatures of 1.5 degrees. So in the case of heat-related mortality, the magnitude of projected heat-related mortality and hazardous heat conditions at 2 degrees is projected to be far greater than at 1.5 degrees. And each additional unit of warming is projected to increase heat-related mortality significantly. And of course, in the context of climate change, there is a need to take climate action, because if we don't, that will have an impact on our ability to achieve a whole range of sustainable development goals, especially that related to achieving good health and well-being for all. And as I said, climate action, taking climate action will help us achieve a whole range of sustainable development goals, not those just related to health. Now, the webinar title has health risk in the title. So I thought it was important to explain what we mean by risk and the drivers or the determinants of risk. Essentially, we can identify three main elements. I should add that this is the IPCC conceptualization of risk. Risk is a product of the occurrence of hazards. And of course, hazards, extreme events occur through natural variability, but human influence, climate change, is likely to influence the occurrence or frequency or nature of those hazards. Risk is very much related to vulnerability, and this is often determined by socioeconomic conditions, standard of living. In the case of heat-related death, age is a very important vulnerability factor. And another element, of course, is exposure. Where we might live, for example, we may live on a floodplain, and that makes us much more exposed to flood events. So it's the interaction between these three elements that determine risk and therefore determine the level of impact or the nature of impacts. Excuse me. Now, there are many pathways by which climate change can affect health. Climate can affect health through direct exposures. Also, there are indirect exposures in terms of health impacts. And through social disruption, also climate change can have an impact on health. But there are other contributing factors as well, and this diagram attempts to describe some of those other pathways. So environmental conditions can also work in tandem with climate change to have an impact on health. Certainly social conditions and the so-called social determinants of health can have a big impact on how health outcomes may respond to changes in climate. And of course, the state of our health systems is also very important. In some parts of the world, health systems are very well developed. In other parts of the world, health systems are not so well developed. So there are multiple pathways through which climate can impact health. Now, generally speaking, we can divide the health impacts into direct ones, those which we have a good level of understanding of the relationship between climate and health, and indirect health impacts. Now, this is a set of health outcomes which we know exist and we refer to as direct impacts. We have a good understanding because lots of evidence has been gathered through research, and there's very high level of agreement between that evidence. So it creates a high level of confidence in us understanding the relationship between climate and health. And some of those health outcomes which we know there are very clear links between climate and health, the impact of extreme events such as hurricanes and floods, they cause injuries and in the worst case, deaths. There are clear impacts from extreme heat and cold events, often manifest or codified in the form of heat waves and cold waves, clear impacts of waterborne disease, for example, diarrhea, vector-borne disease, climate impacts on mosquito populations, and therefore malaria and dengue fever, for example. Climate impacts air quality and therefore can have impact on respiratory disease. And similarly, climate can have an impact on foodborne disease, especially temperature ruining food, and that can lead to food poisoning. So this is an example of some of the direct impacts of climate on health. There are a set of other more indirect or more complex relationships between climate and health. And these are some examples. Food production, for example. Climate can have an impact on food productivity. Droughts can have an impact on the success of agricultural yield and also nutritional status. And of course, that can affect malnutrition through food supply and impacts on nutritional status, impacts on biodiversity, loss of natural food resources, for example, impacts on infrastructure, affecting our ability to access health services, visit family members and offer them support. And also climate has an impact on society. Dislocation, the physical forcing of people away from where they live, impacts on mental health, wider community impacts, and also lifestyle and behavior. We may have to change the type of work we do, for example. So these are some of the examples of the more indirect impacts of climate on health. Excuse me. Now I want to move on and talk a little bit more about climate change, heat and health. I want to talk about heat because heat is one of the most clearly understood ways in which climate impacts health. So through climate change, we're through human influence impacts on the atmosphere, we're increasing emissions. That's going to raise temperatures, has an impact on heat waves, and it will cause a number of extreme events. And there are a number of exposure pathways by which we can affect health. And it's the heat stress exposure pathway, which I want to focus on in the next few slides. Now, generally, we can represent the relationship between heat and temperature and mortality with a U-shaped curve like this. So at lower temperatures, mortality tends to rise, and we refer to that mortality as cold-related deaths. And at higher temperatures, mortality tends to rise, and we refer to those as heat-related deaths. You'll notice there's a range of temperatures in the middle here for which mortality doesn't rise. So we often refer to these as the optimal range of temperatures. So these temperatures for which heat-related and cold-related deaths occur, we refer to as non-optimal temperatures. And of course, we're very interested in these threshold temperatures around here for heat and cold, beyond which mortality tends to rise quickly. Now, the shape of that temperature mortality curve is not constant across the globe. It varies geographically. So if you look at the situation for Beijing, for example, here is temperature along the bottom, mortality up the vertical axis, and we can see the relationship between temperature and mortality. Now for Beijing, we can see a gradual rise in mortality for high temperatures. And this temperature here is sort of around the threshold temperature of 25 degrees. So beyond 25 degrees in Beijing, we see some evidence for a rise in heat-related mortality. You contrast that with the situation for London. You'll see beyond temperatures of 20 degrees or so, that mortality rises rapidly. So the heat response to climate or extreme temperatures in London is far greater than in Beijing. So climate sensitivity varies geographically. Now, every year, an assessment is made of the global burden of disease, the number of deaths we can attribute to different disease types. And this is the results from the global burden of disease assessment for 2019. For 2019, it was estimated that 2 million temperature attributable deaths occurred, which is equivalent to around 3.4% of the total global death toll. Of those 2 million deaths, there was about 1.7 cold-related deaths and just over 0.3 million heat-related deaths. But interestingly, since 1990, there has been a trend in a decreasing burden of cold-related deaths and an increasing burden of heat-related deaths. So clearly something is happening to the relationship between cold and heat-related deaths. And this naturally raises two questions. One question about the present and one question about the future. So a question about the present is, has human-influenced global warming already contributed to heat-related deaths? And of course, a natural question about the future is, what will happen to levels of cold-related and heat-related deaths under climate change? Now, researchers have begun to answer some of these questions. Just want to turn your attention to the legend at the bottom of the figure here, which shows the heat-related deaths attributable to climate change between 1991 and 2018, as measured in deaths per 100,000 population. Now, from that legend, you can see that some countries already are experiencing deaths directly attributable to climate change. Over 3 deaths, Iberian Peninsula, Eastern Mediterranean, Southern Mediterranean, and parts of the Middle East, and indeed Southeast Asia and some parts of South America. So there is some clear evidence based on this study of 43 countries that some places in the world are already experiencing heat-related deaths directly attributable to human-influenced climate change. And just building on what Tianjing said about attribution, and he gave the example of the 2018 summer heat wave in China. There is clear evidence that we can attribute some recent severe climate heat wave events to climate change. And this is an example of the record-breaking 2018 summer heat wave in Japan, in which more than 1,000 people died. And a set of Japanese researchers concluded that this heat wave could not have happened without human-induced global warming. And similarly, the Northwest Pacific heat wave referred to by Tianjing also could not have occurred without the influence of human-influenced climate change. The authors of this study have concluded this heat wave would have virtually been impossible without the influence of human-caused climate change. And indeed, global temperature increases of 1.2 degrees since pre-industrial times made this particular heat wave 150 times more likely. Now, that is a worry because, as Tianjing has shown, with human-influenced climate change and global warming of 1.5 degrees and other levels of warming, the frequency of extreme heat events will not only increase, but their intensity will also increase. So with changes in frequency and intensity of heat waves, and also a growing global population, this means a greater number of people will be exposed to heat in a future warmer world. So this just shows the outcome of some research that looks at the combined effects of different combinations of shared socio-economic pathways and different emission scenarios. So SSP here is an economic development pathway where we continue to develop with conventional means. We don't change the way we are doing things. And you can see the combination of high emissions and continuing to develop as we have done for the past 50 or so years leads to very high numbers expressed in person days on an annual basis of people exposed to heat, especially in these low latitude tropical and Mediterranean climates, and also across the east coast of North America, parts of South America. So in the future, far more people will be exposed to extreme heat. Now, this map shows the current distribution of cold-related annual excess deaths and heat-related annual excess deaths. And we can see, as we've mentioned before, far more people presently die from coal-related deaths. Now, in Europe, some work has begun on looking at the impacts of climate change on the relationship between heat and cold-related deaths. Presently in Europe, cold weather kills 10 times more people than hot weather. So that raises the question, will global warming reduce cold-related mortality because of warmer winters? And will this be a possible positive impact of climate change? Well, the answer to that is yes, possibly, but it's the net effect of climate change on deaths attributable to non-optimal temperatures that is important. And these figures show the outcome of some research done by some European researchers. Here we have the different emission scenarios. There's RCP 8.5. This is the projected temperature under different research concentration pathways or emission scenarios. And we can see the projected temperature through to 2100 under this high emissions scenario compared to a low emissions scenario. This is the same sort of thing, but now in terms of the percentage of total deaths attributable to non-optimal temperatures. And this is the high emissions scenario, and this is the low emissions scenario. And these two figures show the same thing, but now that total percentage broken down by cold-related and heat-related deaths. So you can see under the high emissions scenario, it is projected that cold-related deaths will reduce dramatically towards the end of the 21st century. On the other hand, however, the percentage of deaths attributable to heat will increase rapidly under a high emissions scenario. So this has caused this group of European researchers to conclude that although the percentage of Europeans dying from cold will steadily decrease, the percentage dying from heat will increase. So heat-related deaths will start to exceed the reduction of cold-related deaths into the second half of this century under RCP 8.5. So the net effect is an increase in temperature-related deaths. Now, something which we're really concerned about is the impact of a changing climate on cities and the climate of cities. This map shows the blue circles, the current megacities of the world, cities where there is a population of over 10 million. The purple indicates the megacities of the near future, 2030. And we can see here projections of population for some of those megacities. New Delhi around 43 million, Tokyo around 36 million, and Shanghai around 44 million. The reason why we are worried about the impacts of climate change on the cities of the future is because of the so-called urban heat island effect. Cities are warmer than their surrounding rural environments, and this is because cities and the buildings that make up cities absorb a large amount of energy that comes in from the sun, and that energy is re-emitted back into the urban atmosphere to keep urban temperatures above that of the rural surrounds. And also human activities emit a lot of heat into the urban atmosphere, and we refer to this as anthropogenic heat flux, and that helps keep urban temperatures above the rural counterparts. And we can see that clearly in some satellite images. For example, of Paris, we can see a very warm urban core and a cool sea of air surrounding urban areas of Paris. So this is the urban heat island effect expressed in the form of land surface temperatures. Now we know humans are clearly affecting the climate of cities and the climate of the land surface. And this set of satellite images shows the changes in land surface temperature due to human activities, or otherwise we could refer to as the anthropogenic surface urban heat island. If you look at the case of Beijing, 1986 to 2017, we can see a clear change in land surface temperature directly attributable to human activities. So the thermal footprint of the human influence on land surface temperature has increased significantly with the growth of cities. So clear evidence that humans are impacting the climate of cities. And of course, what we're interested in is the extent to which global warming will affect the climate of cities and to what effect that is going to have on the level of the urban heat island effect. This is the results from some work on the impact of climate change on the climate of cities, so the largest cities in the world, and the climate change compared to 1990. UHI here refers to the urban heat island effect. The solid curve here refers to the change in temperature, you can see on the horizontal axis here, related to global warming only. The dashed curve refers to global warming and the urban heat island effect. So for the case of 2100, you can see just due to pure global warming, for 25% of the largest cities in the world, temperatures will increase by just over 5 degrees. But if we take into account the urban heat island effect, this adds another 2.4 to 2.5 degrees. So by 2100, it is possible that 25% of the world's largest cities will experience increases in temperature of over 7 degrees. And of course, that is extremely worrying. And of course, we know that heat waves interact with the urban heat island effect to amplify the urban heat island effect. This is the results from some work we've been doing in London. Along the horizontal axis here, we have the hours of the day from midnight through to 11 p.m. The vertical axis here, we have a measure of the urban heat island intensity, which is simply the temperature city between the city center and a nearby rural location. This shows the urban heat island intensity for your average summer day or a selection of non-heat wave days. And we can see the urban heat island intensity is around 1.8 degrees in the early hours of the morning. However, when heat waves occur in London, those heat waves amplify the urban heat island effect. And this is the curve for a set of heat wave events. And we can see it adds about another 1.4 to 1.6 degrees, and it amplifies the urban heat island effect up to around 3.2 degrees. So of course, this interaction will continue into the future and is a worry, especially if heat waves become not only more frequent, but far more intense. So this naturally raises the question, how can we adapt to living in a world with more extreme heat? It's very clear that we need to adapt. This is the so-called burning embers diagram used by the IPCC to demonstrate the changing levels of risk and the different adaptation scenarios and sustainable development pathways for different levels of global warming. The yellow indicates that the impacts of climate change are detectable. Red indicates that will be widespread and severe impacts and risks. And purple indicates very extreme risks and maybe irreversible trends in some of the impacts. As we move from left to right across these three columns, we move from low levels of adaptation to high levels adaptation. So if we take the example of a world 2 degrees warmer than pre-industrial times, we can see under a high adaptation scenario and achieving good levels of sustainable development, the levels of risk in a 2-degree world will be far lower in terms of heat-related mortality and morbidity compared to a world where we have low adaptation and it's 2 degrees warmer. So that it's from this type of analysis, it's very clear that if we don't adapt, this is going to affect the levels of risk and associated impact. This slide just summarizes some of the 4 broad types in which we can respond to the threat of extreme heat through behavioral or cultural responses or judgments. We can use infrastructure or technology, and often used strategy, of course, is air conditioning systems. We can take institutional actions through policy, and also we can implement ecosystem or nature-based solutions. I just want to talk very briefly about some of these solutions here in red: climate-sensitive design, heat health action plans, and also green and blue infrastructure. This shows the general structure of a heat action plan, wrapped around a heat action plan, which can be implemented at the heat waves timescale, or it can be implemented in the long term to plan for the effects of climate change. Needs strong governance structures for heat. So we need a government agency, a lead agency, to take responsibility for managing the outcomes of heat. And of course, we need climate resilient health systems. Key parts are surveillance and early warning, and of course, a community response plan and measures. And those warnings and responses apply to especially vulnerable communities. Now, heat warnings are a way in which we can warn the public about the impending effects of heat waves, but also we can think about longer-term sustainable solutions around cooling strategies. This is a typical structure of a heat warning system, which is based on information provided by a weather forecast. So we get forecasts of temperature, humidity, wind, radiation for the coming days. That's fed into a model that tells us something about the likely levels of heat stress over the coming days related to a heat wave, or indeed about the likely levels of mortality or morbidity. So related on some predefined threshold level for heat stress or mortality, the decision is taken whether to issue a warning. And those warnings can be issued to a variety of target audiences. For example, warnings can be issued to the Ministry of Health. Ministry of Health can alert the media, and the media can alert the public. But of course, the effectiveness of these warning systems is very much based on whether the recipients of the information, the public indeed, are listening, and whether people choose to take action. And this is important because there is a very well-known set of ways in which we can respond to the threat of heat. But of course, many of these strategies are based on the success of people listening and taking action. Now, longer term, we can think about so-called climate-sensitive urban design and indeed climate-sensitive city planning. There's a whole range of green infrastructure strategies we can use. For example, green roofs. When we resurface roads, thinking about the reflectivity of the materials we use to resurface roads, because some surface materials are, thermally speaking, hot compared to other materials. And here we can see contrasts in road surface temperature for cool materials compared to so-called hot material. And just by changing the color of the roof of buildings, we can affect the amount of energy which is absorbed by the roof. So light-colored roof surfaces reflect a far greater amount of the incoming energy from the sun compared to dark-colored roof surfaces. And of course, we can use green infrastructure in terms of urban forestry, planting trees, increases shading, increases rates of evapotranspiration, and evapotranspiration is a cooling process. And through blue infrastructure, lakes, ponds, rain gardens, we can also increase evaporation rates. So there's a whole range of things we can do at the building scale and the wider city scale to mitigate the impacts of heat. And of course, whatever we do to reduce the impact of the human influence on climate change has benefits for health. So through so-called climate resilient development, which is the deliberate adoption of mitigation and adaptation measures to secure sustainable development, this will deliver benefits for health. So there'll be many co-benefits, for example, moving to alternative energy sources, improving insulation in our homes to protect us not only against heat, but also cold, encouraging active transport, and so on and so forth. So whatever we do to mitigate the effects of climate change, it will have co-benefits for health and a whole range of other sectors. Now, I just want to finish by reflecting upon some possible lessons learned from the ongoing COVID-19 pandemic. From the pandemic, I think it's very clear that delay is costly in terms of taking action. So an immediate priority, I think, for all of us in terms of climate change is mitigation and adaptation, immediate action around mitigation and adaptation. Also, we must engage with citizens and build trust and understanding with the public about the scientific evidence for climate change, because the actions of many, as we've seen through the pandemic, will make a difference. Also, the pandemic has made it crystal clear that socioeconomic inequalities can result in very damaging outcomes, and that will also be the case for climate change. So it makes it critical that we start to take seriously achievement of many of the sustainable development goals that address inequality. And also through the pandemic, it's very obvious that global problems require global collaboration. And that's why it's critical we get it right at the upcoming COP26 in November in Glasgow this year. And also policy needs to be based on scientific evidence and be non-political or apolitical. It's very clear the science of climate change is well established, and the evidence of human influence on climate is unequivocal. So really, there's no excuse for inaction on climate change. Thank you.
Terrific. Thanks very much, Tianjun and Glenn, for your truly excellent presentations. They were wonderfully informative, inspiring, and perceptive. I'm grateful for your willingness to take questions. We thank the audience for submitting over 110 questions. Some were answered by the presentations, and we'll do our best to cover the key others. Clearly, climate change is seen by all of us as an urgent issue. But as one person wrote, hardly any of those I know are willing to discuss the matter of climate change or contemplate lifestyle changes. Glenn, in your opinion, what steps can be taken to encourage the public to take the issue seriously? Might behavioral science help?
Yes, certainly. There's the adage, think globally, act locally. So through local action and individual action, we can make a difference. And of course, our colleagues in social science and behavioral science can help us understand how people respond to wider policies, not only on climate change policies, on the environment, because there are many determining factors which influence, let's say, the public consumption of science and therefore how they respond to policy. And we can see that very clearly in the case of heat wave warnings. Some sectors of the public will respond to a warning, some will not respond. And indeed, some are totally unaware. So I think social science and behavioral science can really help us understand some of the conditions and determinants which control our behavior and therefore our willingness to get to grips and grasp the implications of climate change. Thank you.
Thanks very much, Glenn. Tianjun, before putting the same question to you, I want to mention that one person noted discussions on climate change in China are secondary to a broader environmental discussion. For example, that on air and water pollution. Tianjun, what is your opinion on how we can encourage the public to take climate change seriously?
Thanks to Junjie for the interesting question. First, I hope to note that the efforts devoted to environmental protection does not contradict with that devoted to mitigate climate change. Because to solve the problem of air pollution, we need to control the emission of aerosols. Both aerosols and greenhouse gases are mostly come from fossil fuels. So efforts devoted to protect climate will not only improve the air quality, but also reduce the consequence of climate change. We know China has seen a tremendous economic transformation since the end of the 1970s or the early of the 1980s. And China has been the world's fastest economy, maybe in the past decades, several decades. The main drivers of this kind of development are the industrialization and also urbanization. This has caused environmental problems, such as the air pollution and the water pollution, as Junjie mentioned. For example, in my field, the sulfate aerosol emission in China has been gradually increased since the late of 1970s. So environmental problem has been regarded as one, maybe the first and the foremost question by the public. So the energy structure should be and also has to be adjusted. This was done in the past decades. So now we have seen a decline of sulfate emissions since around 2008. And now in many parts of China, we have more blue sky and also clean water. Second point I hope to note is that, as introduced in my talk, we now have more evidence of global change. The climate change is already affecting many parts of our climate. So we need to take actions to limit global warming. China has already committed to take carbon dioxide emission before 2030 and achieve the carbon neutrality before 2060. This is now called dual carbon goals in the media. It's also well known in the public. So in recent years, the government has urged a quicker steps to come up with an action plan that enable the peaking time of the emissions. It also calls for an accelerated efforts to better the industrial and energy structures, and also enable the peaking of coal consumption at the early stage. We are also boosted the development of the new energy. So much effort has been devoted to climate mitigation. Thank you.
Excellent. Thanks, Tianjun. Back to you, Glenn. Do you foresee climate change leading to conflicts and or widespread forced migration?
Well, certainly there is the potential for climate change, and especially the impacts of extreme events to cause unwanted or unplanned migration or dislocation of people. So if we take, for example, the impact of sea level rise on communities living very close to the sea on coastal plains, or indeed in the Pacific and the Indian Ocean, living on atoll islands, sea level rise will clearly be a threat to the maintenance of their communities. So climate change certainly has the potential to cause forced migration, purely because people will lose a place to live. And that may become very obvious within the next 20 to 30 years in a number of locations. Of course, increasing frequency of drought may no longer make it sustainable to live in certain locations, no longer being able to grow crops, feed families, so on and so forth. So that may cause people to move. And of course, climate change is going to have a big impact on resources, and water is a classic example. Water is the center of life. We need that to sustain life. So in some parts of the world, there'll be impacts of climate change on water scarcity. So there'll be a competition for a dwindling water resource in some parts of the world, and that may lead to conflict. And of course, there's not only conflict at that very large scale, there's conflicts at the individual scale as well, and impacts on how well we are feeling during extreme heat events can often cause conflict between individuals or small groups of individuals. So there's emerging evidence that extreme environmental events, extreme climate events cause people to move. A very good example is Katrina. Hurricane Katrina in the United States caused large-scale outward migration from the southern states. Many of those people did not return to New Orleans or the wider area. So that was permanent migration as a result of a severe climate event. So there is some evidence emerging that extreme events do have impacts on migration and also possibly conflict. Thank you.
Thanks, Glenn. I now have questions relating to attribution. Firstly, to Tianjun. How reliable are the climate model predictions? And with the extreme precipitation events in northern China in mind, can climate models do a better job of simulating the likely intensity of extreme weather?
Thanks to Jinjie. This is a question is related to my field. We know Professor Manabe is a pioneer in the development of climate models. While the current state-of-the-art climate models are more complex and also far better than the first generation models produced by Manabe and his colleague, we should also acknowledge that the current models still have uncertainty. Generally, for the prediction of the temperature is better than the prediction of precipitation. This is because it's very difficult and also maybe perfect in the description of the convections and the cloud physics in the models. However, we have many ways to correct or constrain the projection. For example, in the IPCC AR6, we have used multiple ways to correct or constrain the projection. This kind of method is based on the observation and also other methods. So in this way, we can give a better simulation. For the simulation of the extremes, it has been a challenge to models, especially for the extreme events such as that you mentioned in North China. Usually, high-resolution models can do a better job in this regard. In particular, kilometer convection permitting models can do a good job in this regard. In addition, we can also use dynamical downscaling and also statistical downscaling to increase the reliability of the projection. Thank you.
Thanks, Tianjun. Now I have a pair of questions relating to future action, the local and global. One is, if there is one action each member of the public can do today to help slow down the damage of climate change, what would that one action be? And at the other end of the scale, if you could make one ask of the leaders at the COP26 summit, what would that ask be? Glenn first.
Yes, thank you. Two very big questions at different scales. At the individual scale, I would encourage people to think how they get about and the means of transport they use, especially if you're living in a smallish city. Active transport is a real possibility. So not relying on the private motor vehicle, or indeed, if you need to commute using a private motor vehicle, think about planning to change to one which is powered by an electric battery. And what I mean by active transport is, cycling, walking, so on and so forth. So, and also using public transport, because that is far more efficient than using private vehicles. So thinking about how we move about, the means by which we move about can have a big impact on emissions, because many of the greenhouse gas emissions, CO2 and others, are related to emissions from fossil fuel driven vehicles. At the global scale, and this is where I think COP26 is extremely important, my encouragement would be to encourage world leaders to sign up to the Paris Agreement or stick to their commitments, the Paris Agreement, and really take on board the urgency of taking climate action and meet their commitments to reducing greenhouse gas emissions. So that would be my key message to individuals and world leaders. Thank you.
Thanks very much, Glenn. Tianjun, what's your view? Thank you.
Thanks to Jinjie. To the public, global warming is real. It's already happening. We can help to limit global warming by using public transit system, by using electric vehicles, and you also use more clean energy. At least we can try to reduce the use of the disposable package. We can do this. Everybody can do this. At global scale, to the world leaders in the coming COP26, one word I want to say is the global warming from the pre-industrial era was caused by human activity. Our difficulty in limiting global warming was partially delayed due to the inactivity of humankind. So we need quick and strong actions now. Why cannot we work together to guarantee a sustainable future Earth? Thank you.
Thanks very much, Tianjun. Due to time, now we need to bring the Q&A session to an end. And I wish to reiterate our deep gratitude to Tianjun and Glenn for their very insightful answers and the great walkthrough of some of the most crucial issues facing us today. Now it is my great pleasure to welcome Professor Xining Chen, Director General of the Chinese Academy of Sciences, and Professor Claire Melly, Pro-Vice Chancellor Global of Durham University, who will give their closing remarks. Over to you, Director General Chen.
Thank you all. Hi, everyone. Yeah, it's my great pleasure to attend this event. Even this is not my major, but I'm very, very interested in this topic, as this is the biggest challenge in the world right now. I want to thank Professor Galen McGregor and Tianjun Zhou for their very nice talks. Even as I think, yeah, for me, okay, I still can understand your ideas, and it's very, very good results. And also thanks during acting Vice Chancellor Anthony Long and Pro-Vice Chancellor O'Malley for your great support. Thanks, Professor Junji Wu. Yeah, you give us a lot of support and a lot of connection. Yeah, without your support, I cannot imagine this wonderful events. And also during the QA session, you did a lot. So you make a very good contribution, yeah, even before and during this webinar. And thanks all the staffs from both sides who contribute to the successful events. I'm very happy that this events, I noticed that we have more than 200 audience during this events. As you know, yeah, this is a big number. Okay, so yeah, you are great talk and also a great attendees. Thank you all. Climate change affects, yeah, everyone on the global, and the upcoming COP 2026 will be happening in Glasgow in next couple of months. Yeah, actually, I just finished my COP 15. Yeah, the topic is about biodiversity, and this is the climate change. So these two topics very closely. So I think it's a very important thing. This webinar is just in I think it's just a right time before the COP 26. The two speakers' talks gave us really informative, helpful to us to understand the human beings' influence on our climate change, the changing nature of extreme events, as well as the consequences of the climate change for our human life and human health. Just as Glenn mentioned, Katrina, when I visit New Orleans, I find that Katrina really changed that city and also the people in that city. You know, that is a very active city before Katrina, but after that one, it's really changed. So that's very impressive for me. I really impressed with Tianjun and Glenn's work, to help us and to understand. I hope they will have more collaboration in the future. Although we are in the step into the end of this webinar, our collaboration in the post-COVID-19 era will continue. I think, with the information technology, we could even collaborate remotely. I hope that we will have this similar face-to-face in next year. I believe that joint efforts from both sides, more contributive, more collaborations will to bring more results, and also generate more knowledge to help us, our community, to improve our environment and against the climate change. Thank you all and stay safe.
Thank you very much, Director General Chen, for your wonderful comments. And thank you to all the speakers for your fascinating presentations. And thank you, Junji, for your excellent moderation of the Q&A session. I echo the thanks of Professor Chen there. My name is Claire O'Malley, and I'm the Pro-Vice Chancellor Global at Durham University. And I'm really delighted to see that this international webinar series and our long-standing partnership with the Chinese Academy of Sciences is really going from strength to strength. We are committed to and proud of being part of a global community of leading researchers who are working together to help tackle some of the most pressing issues in society today. And there cannot be any more pressing an issue than climate change, as has been said. We're very excited to continue this work and further expand it. It's great to see that so many of you, over 250 from so many countries, were able to join us today. So thank you. I really hope you enjoyed the webinar. As Professor Anthony Long said at the beginning, this is our 4th webinar in this series, and we have further talks planned. So you can keep up to date with the series via our website, and you'll see the link on our closing slide shortly. We'll also send you the recording of today's lecture, which you're very welcome to share, and please do share with your colleagues. We'd love if you could join us next time, but for now, I'd like to bring this webinar to a close and thank you all once more for attending.